All right, so now that we're on our way to being rock stars with row operations and Gaussian and Gauss-Jordan elimination, we're going to talk about inverses and determinants of matrices. So determinants is boy, and I'm making finger quotes now, it's sort of an old process, used to be used a lot more, still used, but not as much as before. Inverses, on the other hand, uber important. So we're going to build that concept first. Before we talk about inverses and how they relate to matrices or inverse matrices, let's just talk about inverses in general to make sure we're getting what we're dealing with. If I have an equation 2x plus 3 equals 6, I use inverse operations to solve for the value of x. I have to first subtract 3 from both sides. When I subtract 3 from both sides, I'm using the inverse or opposite operation to enable to do that. So instead of a plus 3 on one side, I subtract 3 from both sides, which undoes the 3. So I have 2x equals 3. And now when I want to eliminate the 2 from the left-hand side, I use the inverse, or let me rewrite that. I multiply both sides by the inverse. So I have a 2. The inverse of 2 is 1/2. If I multiply both sides by 1/2, this side, I eliminate the 2 by making it equal to 1, and x equals 3/2. So that's just using inverse operations of numbers in order to solve for an equation. We're going to do the same thing with matrices, use inverse matrices to solve for unknown linear systems. Further, remember back here where I multiplied by 1/2, 2 times 1/2, and I said I was multiplying by the inverse. Well, we know that 2 times 1/2 equals 1, and that's the identity element. Under multiplication, where 1 is the identity, any operation that gives me the identity is an inverse operation under multiplication. Under addition, the identity element is 0. If I wanted to disappear my 3 on this side, what I basically did was subtract 3. So under addition and subtraction, the inverse element, or the opposite, yields the identity under addition and subtraction, which equals 0. So let's take these concepts and move them into our matrix computations. If I had the 2 by 2 matrix where I have reduced it or been given it in reduced row echelon form, where I have a lower triangle of zeros, an upper triangle of zeros, and a diagonal of ones, this is the identity of the 2 by 2 matrix. So all 2 by 2 matrices, this would be their identity element. If I can reduce a 2 by 2 matrix to its identity, then I've basically been able to do the same operations I do with real numbers, only I've done them with matrices. A 3 by 3 again, I have a lower triangle of zeros, an upper triangle of zeros, and a diagonal of ones. This would be the 3 by 3 identity matrix. And of course, that could go on forever to a 20 by 20 identity matrix, which I will not be drawing. But there is a generalized way to refer to matrices. So in this first 2 by 2 matrix, I would refer to this as the identity matrix with a sub 2, meaning it's a 2 by 2. This would be the identity matrix with a sub 3, meaning it's the identity of a 3 by 3 matrix. And then the generalized form gives us these dotted areas, just like when we remember writing polynomials in their general form. I'm able to expand or identify that a square matrix has an identity no matter how many zeros I have in the first row after the one element in the top left-hand corner. And then same thing here. Goes on and on. Same thing for column length. And then I'd have a 1 in the diagonal. And so this is the identity with n rows and columns. And these are for square matrices, so I don't need an n by m, because no matter what, they're going to be n rows and columns. So remember, working with equations in the real numbers, I would check to see if two equations are inverses of each other. For example, 2x plus 3 equals y, and we have a couple of operations. One is either find the inverse by switching the variables and solving for it, or sometimes I'd be given two equations. Let's see, x over 2 minus 3. This is definitely not the inverse, but just to make the point, if I plug one equation into the other and it reduces to x, I'm halfway to proving that these two equations or functions are inverses. If I do the same thing in the reverse direction and get x again, then I can say that these two functions are inverse functions. So we have a couple of ways to look at inverses. One is to see that if I multiply two values together and I get the identity element, I have an inverse. Or if I multiply functions together and get the x out of each side in each direction, then I have an inverse. So we have a way to find inverses for matrices as well, and it correlates more directly to this method. So let's do an example to see. So I'm given two matrices. A is 5, 6, 4, 5, and B is 5, negative 6, negative 4, 5. The method to determine whether two matrices are inverses is to multiply them. Well, let's put this over here. If A times B is the same value, output value, as B times A, and if that output value is the identity, then we know we have inverse matrices. So let's go ahead and set this up. The first time I'll do it using the shorthand of predicting the size and using addresses to find values for multiplication. I have a 2 by 2 matrix and another 2 by 2 matrix. So these two values are the same, which means they are multipliable. I can multiply them together, and the outcome is going to be a 2 by 2. So A is 5, 6, 4, 5, and B is 5, negative 6, negative 4, 5. And I know that my result is going to be a 2 by 2. So I'm going to put in my addresses to help me multiply. Row 1, 1, row 2, column 1, row 1, column 2, and row 2, column 2. All right, so first I want row 1, column 1. I'm going to multiply row 1, column 1. 5 times 5 is 25. Row 1, column 1. 6 times negative 4 is negative 24. So now row 2, column 1, row 2, column 1. 4 times 5 is 20, and 5 times negative 4 is negative 20. Row 1, column 2. So 5 times negative 6 is negative 30, and 6 times 5 is positive 30. And now row 2, column 2. 4 times negative 6, negative 24, and 5 times 5 is plus 25. So let's simplify. And I have 25 take away 24 is 1, 20 take away 20 is 0, negative 30 plus 30 is 0, and negative 24 plus 25 is 1. So in one direction now, I have shown that this is an identity. Or in one direction, multiplying in one direction or working in one direction, I've gotten the identity out. So now I have to do the same thing in the opposite direction. And this time I'm not going to use the shortcut step. I'm just going to multiply. So this is A times B. So this time I want to do B times A. And B is 5, negative 4, negative 6, and 5. And A, 5, 6, 4, 5. Okay, 5 times 5 is 25. Negative 6 times 4 is negative 24. 5 times 6 is 30. Negative 6 times 5 is negative 30. Negative 4 times 5, negative 20. 5 times 4, positive 20. And last but not least, negative 6, negative 6. Well, wait, 2, 2. Row 2, column 2. Negative 4 times positive 6, negative 24. And 5 times 5, positive 25. 25 minus 24 is 1. 30 minus 30 is 0. Negative 20 plus 20 is 0, and negative 24 plus 25 is 1. So I have gotten the matrix, or the identity matrix, by multiplying B times A. So I can say A times B equals B times A, and that equals the identity, and I could put a 2 because it's a 2 by 2 matrix. And so I can confirm that these matrices are inverses of each other. All right, so that was easy enough. You were given two matrices and a method to find whether they were inverses of each other, very similar to being given two functions and a method to find if they were inverses to each other. But what happens if you're given one matrix and you're asked to find the inverse of that matrix? Turns out we have a method that's very similar to this method. So let's find the inverse. I'm going to be given matrix A equals negative 4, 6, 3, negative 5. So the method we're going to use is we're going to set up a kind of an augmented matrix. And we're going to make use of the fact that all the operations that would convert this to the identity are the exact same operations that would convert the identity back to the inverse. So we're going to work just on this first part, turning negative 4, 6, 3, negative 5 into the identity matrix, and then we're going to keep doing the operations on the identity as we go. So let's see what happens. I want to multiply the first row times negative 1, just so I get a positive 4 here. Okay, then I'm going to add, I'm going to add negative 1 times row 2 to the first row. So the row that's not going to change. And now let's do our subtraction. Negative 1 times 3 is negative 3 plus 4, 1. Negative 1 times negative 5 is 5. Minus 6, negative 1. Negative 1 times 0 is 0, minus 1. Negative 1 times 1, negative 1 plus 0. Okay, so far so good. Now, I want to get a 0 here. So I'm going to add negative 3 times row 1. So the row I'm not changing. Let me be neater about that. Okay, now negative 3 times 1, negative 3 plus 3 is 0. Negative 3 times negative 1 is 3. Minus 5, negative 2. Negative 3 times negative 1 is 3, add 0. Negative 3 times negative 1 is positive 3, add 1. Almost there. I'm going to divide this row by, well, I'm going to multiply the first row by 1. No, I'm going to divide this row first by negative 1/2, or multiply it times negative 1/2. Trying not to do too many steps at one time. So negative 2 times negative 1/2 is 1. 3 times negative 1/2 is negative 1. 3 times negative 1/2 is negative 3/2. 4 times negative 1/2 is a negative 2. And now I'm going to use this 1 to turn this position into a 0. And I'm going to do that by adding row 2. I don't have to multiply row 2 by anything because negative 1 plus 1 equals 0. So the row I'm not changing and the row I am changing. 1 plus 0 is 1. Negative 1 plus 1, 0. Negative 1 minus 3/2, so that's negative 2/2 minus 3 more halves is negative 5/2. Negative 1 minus 2 is negative 3. So there I am. I have converted my original matrix into the identity, and in the process of carrying out the exact same row operations, I've converted the identity into the inverse. So this is the identity matrix. This is A inverse, and the matrix we started with is A. So that finishes our lesson on inverse matrices, finding the inverse and determining whether two matrices are inverses of each other. And now the next video will cover determinants.